Hi, my name's Jacob Wilson, and I did my project on the planets beyond ours, and how mass, volume, and habitability changes based on how far out they are from their stars. An exoplanet is considered to be any planet outside our own solar system, and is not one of the 8 or 9, depending how you feel about Pluto, that we learned about in elementary school. This data comes mainly from NASA's Kepler mission using the Space Telescope, and has increased the number of exoplanet discoveries so we can do a project like this. The purpose of this project is to help us to understand these planets, which would thus help understand our own planets and solar system, and to expand the search for other habitable planets similar to Earth. The independent variable of the project was orbital distance, which is how far out an exoplanet orbits from its stellar host or star. For example, our Earth orbits 1 astronomical unit away from our own star. I had 3 dependent variables. The first was planetary volume, while the second was planetary mass, which relates relatively closely, and the third was habitability, which is defined as the planet's ability to carry liquid water based on the luminosity of its star that it orbits. So the hypothesis for this project, I had 3 sets due to my 3 dependent variables. My first was for mass, which the null hypothesis states that there is no change in mass as distance changes, while the alternative states that mass increases and then decreases at the last increment as distance increases. With planetary volume, it was the same thing, with the null hypothesis being that volume does not change as distance increases, and the alternative stating that volume increases and then decreases at the last increment as distance increases. With my last hypothesis about the habitability, that the habitability does not, the likelihood of a planet having habitability does not change as distance increases, while my alternative is stating that a planet is more likely to be habitable the closer it is to the star. So my reasoning for this with my mechanisms is empirical data from our own solar system. It's the system we have studied the longest and the most in detail, and this is the same pattern we see within it. The second is the current theory of the solar system formation, which is the nebula theory. And how it is that there's a stellar cloud of dust with a bunch of basic elements that are used to form stars, and an external force causes the cloud to collapse, and it creates a spinning disk, which we can still see today with how our planets orbit around. The pressure from the collapse allows for fusion between hydrogen atoms to create helium, which fuels our sun, as we all well know. And the sun then continues to use more material, but however the remaining material and matter is drawn together, creating planetesimals, and then thus the planets that we know today. And this is the primary theory of how planets and thus solar systems are formed. Now, how this relates to my hypotheses is that if you are closer to the sun's more likely to use the majority of the matter, leaving less for planets to be formed. Thus is why Mercury is so small, and Jupiter is so big, because Jupiter is in the middle. And the further you would get out, the less matter there would actually be due to gravitational attraction, which is why Neptune is relatively small to Jupiter. Now, I was not able to get my own space telescope, nor did I have the time to do this project, so I had to use databases from other sources. One such database was the NASA Exoplanet Archive, and with the other being Simbad, which I used to find my stellar data. Now, the way that NASA collected this exoplanet data was with this Kepler Space Telescope. And how this works is it finds a field of vision. It uses primarily the transit method. The transit method is the most recent method that we've discovered that allows us to exponentially increase our discoveries of exoplanets. While we do have other methods that we used in the past, they are not used as frequently, for they're not as effective. These methods include radical velocity, timing variations, gravitational microlensing, and direct imaging. Now, how the transit method works is the transit describes how when a planet passes in front of our perspective of a star, This causes a dip in the brightness of the star, and thus if we have a telescope pointed at a wide range of stars, we can observe any dips in the brightness of the star, and depending on the consistency and the frequency of the dip, we can then determine if there's an exoplanet there and the characteristics of said exoplanet. So here are my data on the mass of the planets, with the x-axis being the distance from the stellar host or star that the planet had, with the y-axis being its mass. Each dot represents an individual planet, and as we can see from the trend line, it's relatively non-changing. So in order to do an accurate statistical analysis, we ran a logistic transformation on the data, with the x-axis still being the distance and the y-axis being the log of mass. So this gives us a trend line with a little more slope, a slope of 0.2398 to be exact, with a p-value of 2.2 times 10 to the 10th. Now the statistical ran was a logistic regression with an alpha of 0.99. So this data is significant. With the volumetric trends, once again we see a similar pattern, and the x-axis once again is the distance from the stellar host, while the y-axis this time is the volume in kilograms cubed. Once again, our trend line is relatively non-changing throughout, so that logistic transformation was changed. However, this time we see less relationship between the data, and this is also represented in the relatively non-changing trend line, which appears to be slightly negative in this case, with the slope of the trend line being negative 0.1712. Logistic statistical test was ran with an alpha of 0.99, giving us a p-value of 0.0094, which is still significant. With the habitability of the planet, the x-axis is once again distance from the stellar host that the planet orbits. However, this time the y-axis is the z-score from the ideal habitability orbit, and what this means is that the habitability zone has an upper and lower inclination. These act as the z-scores 1 and negative 1, and the z-score of the planet's orbit within this was calculated and then thus plotted for it. We can see this a little more in detail here, with the upper inclination being 1 and the low inclination being negative 1, with the light blue dots being the ones within the habitability zone and the dark blue dots being the ones outside habitability zone. We see some go over the line where they're not supposed to, because of the fact that the orbit distance is an average. So there is periods that it may go in habitability and then out once again during another season. A logistic transformation was conducted for more accurate statistical analysis, and this, once a logistic regression was ran with an alpha of 0.99, it gave us a p-value of 0.215, which is not significant. So in summary of the results, the orbital distance of a planet does have a significant effect on the planetary mass and volume. So for these hypotheses, I reject my null hypothesis. However, with the habitability, the orbital distance of the planet does not have a significant effect on it, and I fail to reject my null hypothesis for this. Now, the implications of this data, we can use these data and the equations we get from the graphs to locate planets based on particular parameters, such as mass and volume. So if we wanted to find a planet with the mass of Jupiter per se, we know about which range of distances to look within each star. Now with the habitability of the planet, I found that 6.04% of the planets within this data set are habitable. This means approximately out of every 100 planets we will find will have the ability to support water. This means a great deal about the potential life and colonization efforts in the far future. Now we can also, most importantly in the short term, we can use this data for comparisons between individual solar systems, such as the number of planets, for example. I found that most systems have about one planet, or only one planet in them, about 1900, while other systems I only found one system with 7 planets. So this makes our system with about 8 or 9, about depending how you feel about Pluto, to be extremely rare and unique. We can also look at how these systems form. If we see a similar pattern, it'd be wise to infer that they form in a similar or the same fashion. Where we can also find planets with the habitability and the mass and volume of Earth for Earth-like planet studies. If we find an early Earth-like planet, we can use it for geological history study. We can also use it for climate change study if it's undergoing a process, but in a more advanced stage. Now, we can also use this data as collectively for parallels and comparison between galaxies, our galaxy, the Milky Way, and others. We can use the mechanism of the formation of the solar systems within each galaxy. If they're different by galaxy, perhaps we can infer that the galaxy formation influenced solar system formation, or any or a similar way. We can also look at any fundamental difference between planets, like if we find more habitable planets in, say, the Andromeda Galaxy versus our own Milky Way galaxy. And what all this data really leads to is us finding our own place in the universe and how unique we are. So what I want you to remember, out of all the planets that there are, and out of all the planets that are our size, and out of all of them that have the ability to support life, we're the only ones that we have found so far with that support life and intelligent life as well.